Hey there guys, welcome back to Vector Calculus. I'm Mike back here coming at you with another video. In the previous video, we had talked about the derivation of the formula for the surface area of a three-dimensional surface. Today we are going to get into some examples as to how do you use this formula to actually calculate that surface area. So just as a quick recap, if we have a 3D surface S, then the area of that surface is the double integral over d, which is the region in the UV plane, of the norm of the cross product of t sub u hat and t sub v hat, and that is the integral dv du. So the first example that we're going to do is we're going to prove a basic surface area formula that's out there. This is a nice first example because we'll know the answer we should get. We're just going to see how we get to that. So we're going to prove the formula for the surface area of a sphere of some fixed radius r. First thing we need is we need a parameterization for the surface. We need a parameterization for the entire sphere of some fixed radius. Well, this is one of our basic sets of parametric equations that we should know. The parameterization for a sphere with a fixed radius r is capital phi hat of u comma v is r times the sine of v times the cosine of u, comma r times the sine of v times the sine of u, comma r times the cosine of v. And the bounds on our parameters u goes from 0 to 2 pi and v goes from 0 to pi, as we can see here. So we need the partial of capital phi hat here with respect to each of u and v. These are going to be our t sub u hat and our t sub v hat. So if I take the partial of capital phi hat with respect to u, that gets me t sub u. And that's going to give me minus r times the sine of v times the sine of u, comma r times the sine of v times the cosine of u, comma 0, because there's no u's in that last part there. And if I take the partial of capital phi hat with respect to v, that gets me t sub v hat. And that's going to give me r times the cosine of v times the cosine of u, comma r times the cosine of v times the sine of u, comma minus r times the sine of v. So these are the two partials that we need. We're now going to take the cross product of these two vectors. Just going to rewrite all this here. Again, the cross product of two vectors is simply the determinant of a 3 by 3 matrix. And what this is going to turn into is I hat times its minor, which is the determinant of the resulting 2 by 2 matrix. So A times D minus B times C. Well, R times the cosine of B times the sine of U times 0 is just going to give me 0. So it's just going to be this product here, which is minus R squared sine squared V cosine U minus J hat, and now times the minor, A times D minus B times C. Again, this product is going to give us 0, so it's just this product right there, which is going to be R squared sine squared V sine of U plus K hat times its minor, A times D minus B times C. This time we're going to get a little bit more. R squared times sine squared V times sine U times a, oh, my apologies, that is a R squared times sine V times cosine V times sine squared U minus R squared times cosine squared U times sine V times cosine V. And now as we write this all as one vector, we are going to come up with minus R squared sine squared V cosine U, comma, minus R squared sine squared V sine U, comma, R squared minus R squared sine V cosine V. So this is where we're at so far. We have the cross products of these things that we need, but now we also have to take the norm of this cross product. We have to take the norm of this vector. And this does look really ugly right now, but we'll see that as we work with our sine squareds and cosine squareds, we're going to see that things do nicely cancel out, and we get it down to something pretty friendly. So it's going to be the square root of the sum of the squares of each of these components. A whole nice big square root, and what we're going to find in the end, that after you multiply everything out and you pull out common factors and combine everything, you come down to R squared times the sine of V. So there's a little bit of algebra that has to be done in there, but what you should come down to in the end is R squared times the sine of V. So this is what we're going to take the integral of. This is the integrand in our surface area formula. Now, we specified our u and v bounds before. U went from 0 to 2 pi, v went from 0 to pi. So making sure that you place the proper bounds on the proper integral. Inside matching with inside, these should be our v bounds there, and outside matching with outside, on the outside should be our u bounds. So this is the integral that we have left to calculate. And this is nothing that is too bad here to really work with. The r is fixed. R is just a fixed constant, so we can pull that outside of our double integral. So now we have to take the integral of sine of v dv. Well, this is just a basic Calc 1 type of integral. The integral of sine v is minus the cosine of v. If we plug pi in for v, we get minus the cosine of pi, which gives us a positive 1. Minus, if we plug in 0 for v, minus the cosine of 0 is a negative 1. So we have r squared times the integral from 0 to 2 pi of 2 du. Well, this is nice and basic, nice and easy. The integral of 2 du is 2u. And if we take our top bound and plug it in, we will get a 4 pi. If we take our bottom bound and plug it in, we'll get 0. So this is going to give us 4 pi r squared. And that is identically the formula for the surface area of a sphere with a fixed radius r. So this is just a nice little check, if you will, to see that the formula that we are using does indeed give us what we should. So just one more case of mathematics taking something that can be very easy and making it much more complicated. So this is just a basic first practice problem of working with something that we know what we should get. The next example that we're going to see, we're going to work with a function of x and y, and we're going to calculate the surface area of this function over some particular region in the xy plane. All right, guys, so we're back with our second practice problem involving the area of a surface. This time we're going to be working with a function of two variables, and we're going to see how we calculate the surface area in this particular case. So the problem that we have here is we're going to find the area of f of x y equals 4/3 times x raised to the power 3/2 minus 2/3 times y raised to the power of 3/2. And we're going to find the area of the surface over the rectangular region. X goes between 0 and 1, and y goes between 0 and 1 as well. So first thing we always need to start off with, we need some kind of parameterization for this surface. Now, for a function of x and y being your surface, your parameterization, pretty nice, pretty straightforward. Capital phi hat, function of u and v, is just u, comma, v, comma, and then your function. Except u's are taking the place of x, v's are taking the place of y's. So u, comma, v, comma, 4/3 times u to the power 3/2 minus 2/3 times v raised to the power of 3/2. We're going to take the partial of capital phi hat with respect to u and v. Those are going to give us our t sub u and our t sub v once again. So partial of u with respect to u is 1. Partial of v with respect to u is going to be 0. And the partial of our third component, or our third coordinate function, is just going to be a 2 times the square root of u. T sub v hat, partial of u with respect to v is going to be 0. Partial of v with respect to v is going to be 1. And then the partial of our function with respect to v is going to give us minus the square root of v. Set up our 3x3 matrix, and we're going to take the determinant of this matrix to come up with our cross product. I hat times the determinant of a resulting 2x2 matrix. 0 times anything gives me 0, minus 2 times the square root of u times 1 gives me minus 2 times the square root of u. Minus j hat times determinant of resulting 2x2 matrix. 1 times minus the square root of v is just minus the square root of v. 0 times anything gives me 0. So we have minus the square root of v. And then plus k hat times 1 times 1 is 1, minus 0 times 0. So that just gives me a nice big 1. So that means that our cross product vector here is minus 2 times the square root of u minus the square root of v, comma 1. We're going to take the norm of this vector here. And we're going to find that we come out with something fairly nice. We get the square root of 1 plus 4u plus v. So this is going to become the integrand in our double integral, and taking the double integral of this is what's going to give us our surface area. So double integral of square root of 1 plus 4u plus v dv du. We just need to substitute in our bounds. Well, we said at the beginning of our problem that x and y both went from 0 to 1. Since x was equal to u and y was equal to v, then u and v thus both go from 0 to 1. So we're integrating with respect to v first. This is a very low level u substitution that's going on here. But what you're going to come up with is 2/3 times 1 plus 4u plus v, that quantity raised to the power 3/2. I can pull the 2/3 out of my fraction and substitute in my top bound first. That is going to give me a 2 plus 4u raised to the power 3/2 minus, when I plug in 0, I get 1 plus 4u. Raised to the power 3/2. So now I'm taking the integral of this guy here with respect to u. Just going to rewrite this for everyone. So we're taking the integral of each of these two terms with respect to u. Now, these guys on their own, these are two very similar, again, low-level u substitutions. If I set what's inside of these things equal to what my u would be, we're just going to have to multiply by the appropriate multiplicative constant. So when you perform the u substitution, which you should all know how to do by this point, you're going to get two fifths times 1/4 times 2 plus 4 over u raised to the 5/2 minus 2/5 times 1/4 times 1 plus 4u raised to the power 5/2. I'm going to simplify all these multiplicative constants. In both of these terms, we have a 2/5 times a 2/3 times a 1/4. Those all just multiply out to 1/15. So If I plug in my top bound of 1 for u in both of these two terms here, I'm going to get 6 to the 5 halves minus a 5 to the 5 halves minus, now I'm going to substitute in 0 for u. That's going to give me 2 to the 5 halves minus a 1 to the 5 halves. Well, 1 to any power is 1. And while this is not the most pretty answer, this is still a final numerical answer that we can work with. Surface area should always be a positive quantity because we have no sense of a negative value of area here per se. So this should be giving us a positive quantity because for the most part we'll be working with functions that lie above the xy plane, so the surface area will be a positive quantity. So these are just a couple samples on how do we use the formula that we derived in the previous video to calculate the surface area of some basic surfaces. In the next video, we're going to begin to talk about the integral of a real valued or scalar function over a surface, and those guys will be surface integrals. It's going to be very similar to arc length versus path integrals. So if you have a question or comment, leave it in the comment section below. Otherwise, keep chugging on, guys.